Okay, the next topic in our series is the Schrödinger equation and quantum mechanics. When it comes to quantum mechanics, the first thing that comes to the mind of any person is that it is something related to the Schrödinger equation. But in our series, we will first look at some of the postulates of quantum mechanics before we can move on to the Schrödinger equation for some solution. Okay, when it comes to quantum chemical methods, we can say that quantum chemical methods imply a quantum mechanical treatment of electrons without resorting to parameterization. If you recall, we have previously said that the semi-empirical methods, they are taking some parameters from experiment. But in ab initio methods, we said that we are calculating everything from the wave function and starting from scratch. It means we are not taking any assistance from any experimental data. So quantum mechanical methods are also called as ab initio or first principle. They can also be called as electronic structure methods or molecular orbital calculations. The question arises, what do we get from these calculations? We know that wave function contains all information inside it. So electronic wave function contains all information regarding the system. It can calculate electronic energy, which can be useful for exploring the potential energy surface that we have seen in the previous lectures. Or it is needed to calculate reaction energies and barriers, and we have also seen some examples in this regard. Electronic wave function can describe the changes in electronic structures and bonds, and we can study changes in molecular orbitals. Electronic wave function can also calculate other properties related to electronic structure, such as various spectra. It can approximate quantities like atomic charges and bond orders and reactivity indices. So we can talk about a bit of comparison between classical mechanics and quantum mechanics. When we talk about classical mechanics, objects are treated as particles with well-defined positions and momenta, and the behavior is governed by Newton's equation or something equivalent to that. And most of the classical mechanics, the fundamental equation is F is equal to ma. And it is appropriate for objects ranging from atoms to planets. So it means it has quite diverse application. It can be applied to atomic system or like molecular system. It can be applied to system as big as universe. Now, on the other hand, quantum mechanics, which is mainly developed by Heisenberg or Schrödinger, objects are described as probability distribution. We know that we have wave function, which contains all information about a system, but if you square it, it gives you the probability of finding an electron in that area. It cannot know exactly a particle's position and momentum simultaneously, which is according to Heisenberg uncertainty principle. All information regarding the system is contained in the wave function, and wave function obtained through Schrödinger equation or something equivalent to that. And it's needed to describe the behavior of small light particles such as electron, maybe protons. Now, the behavior of small particles like electrons, protons, cannot be determined by classical mechanics because in classical mechanics there is no electronic structure. It is simply a ball for atom and spring for bonds between them. Now we are going to see some of the postulates of the quantum mechanics which may be used in the lectures which are going to come in the next few classes. So the first postulate is, or the state of a system is described by a function. For example, psi here. Now then brackets you will see r and t. It means this wave function is dependent on coordinates, electronic coordinates, and t is for time. So we'll see that wave function will be a function of either coordinates or both coordinates and time. Now this is time dependent wave function. Now this is called a wave function. Now this psi here is a single valued, continuous, and quadratically integrable. So it means that the probability that the particle is in volume d tau at position r and time t is like psi star, which is also known as psi conjugate of this wave function. Now you can see this is conjugate, this is original wave function, and it is d tau. It means we are going to integrate it over entire space. Since the particle must be somewhere all the time, so it means if you integrate it, the answer should be equal to 1. Now, this is wave function and it is conjugate wave function, and collectively they are also known as square modulus. Now, it indicates complex conjugate of psi. This is like bold R, which indicates vectors for x, y, and z. D tau indicates integration over all coordinates, and now this conjugate wave function is equal to exponent minus iota 2x. So this iota is square root minus 1. Now the second postulate says that every physical observable is represented by a linear Hermitian operator. Now what is Hermitian operator? There are two different types of operator. One is called as linear operator and the other one is called as Hermitian operator. Now the question arises, what is an operator? It's a rule that turns a function into another function. And the easy way to identify an operator is to see a cap on top of an alphabet. For example, if you see capital D cap here, this cap is an indicator that this one is an operator. Now let's say this operator is an operator for differentiation. Let's say we talk about partial derivative with respect to x here, and we're applying it to some function here, which is function is x squared. Now, if you apply this operator on this function, it means you are going to talk about partial derivative of this x squared. So now applying operator on a function, it means we're talking about curly x squared over curly x. If you do partial derivatization, the answer is 2x. Now you can see here, it's an operator which has operated on this function and gave you this value. Now you have two different types of operator available. An operator with the following properties: operator function x plus gx is equal to operator function x plus operator gx. So it means it can apply linearly on both of them. That is why it is called as linear operator. So operator C fx is equal to C operator fx. So again, this is an example of linear operator. Hermitian operator is something different. It has the properties shown like this here. Let's say if we talk about integration f conjugate operator g d tau, that is equal to integration g operator f conjugate d tau. So the benefit of this Hermitian operator is that it guarantees real values for associated properties. And this is what is required in quantum mechanics, that we can get some real values for associated properties when we solve for the equation quantum mechanically. So every physical observable, according to postulate 2, is represented by a linear Hermitian operator. So quantum mechanical operators are analogous to classical expression. For example, if you talk about kinetic energy, classically it is shown as 1 over 2m px square plus py square plus pz square. Now, in this case, in quantum mechanics, px is equal to minus iota h curly over curly x. So if you bring this equation, a value of px inside this one, the equation for kinetic energy is equal to this one here. And if you combine all of them together, the kinetic energy shown quantum mechanically is represented by this equation, which is very much similar to the classical equation here. So the third postulate says in any measurement of the observable associated with operator B, the only values that will ever be observed are eigenvalues that satisfy this equation. So operator operating on wave function delivers eigenvalue, and the wave function or the eigenfunction is given back here. So operator operating on eigenfunction gives back the eigenvalue of this operator B, and the associated eigenfunction B is also retained there. It is also called eigenstate. Now, psi I is an eigenfunction of operator B. If operating on psi I with B gives back psi I multiplied by a constant, that is the eigenvalue. The constant is called as an eigenvalue, the value of property B when system is in state I. So example is shown here. Let's say if you talk about operator is partial derivative, it is operating on this wave function, which is e power minus 2x. Now, if you apply this operator, operates on this wave function, it means we're talking about this partial derivative. It gives back minus 2 from this differentiation along with the value of e power minus 2x, that is the original wave function. So the condition in this case is satisfied this one. The eigenfunction of Hermitian operator are orthonormal. Orthonormals mean if you have two different, like I or j here, if you have wave function psi j and its conjugate wave function psi I star, and if it is integrating over d tau, it gives this delta value, and this delta value, like I is equal to j, then it should be equal to 1, and if I is not equal to j, it is 0. So that is known as orthonormality. Orthonormal is actually a combination of orthogonal plus normalized. So if a function is orthogonal as well as normalized, it is known as orthonormal. Now, in the case of orthonormal, if I is equal to j, then value is equal to 1. Otherwise, it is 0. Basically, it says that system is in state I or j, but not both. It means it is not possible for this system to be in both states simultaneously. It can be one of them, I or j. Now, let us calculate the eigenvalue for a given state. Let's say we talk about this operator operating on wave function psi I gives value bi into psi I. So let's say we apply this form here. We take this wave function, apply its conjugate wave function, and then integrate over it. We can get ultimately bi delta ij. So delta ij is equal to 1 if I is equal to j. So if that is the case, then bi is equal to this value here, and that is shown here. That bi is equal to integration conjugate wave function operator wave function d tau. The fourth postulate says that an arbitrary state psi can be represented as a linear combination of eigenfunction of a quantum mechanical operator. Before I move forward, I would like to tell you that you will see this postulate 3 applied at a number of positions in the later slides. And this postulate 4 is also applied a number of times in later slides, especially when we are talking about linear combination of atomic orbitals. So an arbitrary state psi can be represented as a linear combination of eigenfunctions of a quantum mechanical operator. So it means you can represent this psi here as a summation of Ci psi I. So these are individual components which are combined together to give you a overall wave function psi here. So this an arbitrary state can be represented as a linear combination of eigenfunction of quantum mechanical operator. And that is also called as superposition principle. So system must adopt a specific state upon measurement. Now, the fifth postulate says that average value of property B at time t is equal to this one. So average property is integration conjugate wave function operator wave function and d tau. So the last postulate here is the time development of a state is given by time-dependent Schrödinger equation. Now, if I include time here in the wave function, it will become time dependent. If I don't include time here, it becomes time independent. In general, when we talk about Schrödinger equation, it is time independent, but we can also include time to make it time dependent. So H is Hamiltonian. This H is Hamiltonian. That gives the total energy operator. Hamiltonian is a total energy operator. So energy is equal to kinetic plus potential energy. So operator is equal to kinetic energy part that we have seen in one of the previous slide and the potential energy part that we have seen in the case of potential energy surface diagram. So kinetic energy part plus potential energy part, total it gives you the Hamiltonian operator. For most chemical problems, V is independent of time. We have seen previously that potential energy does not depend on time, but kinetic energy, it may depend on time. So Hamiltonian operator is equal to kinetic energy plus potential energy, and this is usually called as Coulombic potential. So energy of state specified by wave function is constant all the times, and potential can be given as Q1, Q2 over 4 pi epsilon R12. So we can write here the Schrödinger equation that Hamiltonian operator operating on wave function, which is a function of coordinates and time, it can give you back energy, which is eigenvalue, multiplied by this wave function into RT. Now, if you put the value of Hamiltonian operator from the previous slide, you can get this equation where psi r is the solution to time-independent Schrödinger equation. So this Hamiltonian is time-independent Hamiltonian, and the wave function is time-independent wave function. So summary of quantum mechanics that we have seen so far, solving the time-independent Schrödinger equation gives us the energy and wave function. The wave function contains all the information that can be known for the system. There's a different wave function for each state, and wave functions are orthonormal. The square of the wave function is interpreted as probability. You can see the probability is equal to wave function, conjugate wave function into dRi. So PR is the probability of finding the electron in volume element dr1 at position r1. So we can calculate properties by operating on wave function. Operators are analogous to classical expression for properties. The values of the properties are eigenvalues of the operator. This wave function is an eigenfunction of the operator. The value of the property for the specific state is Bi, which can be given as wave function, conjugate wave function, or square modulus multiplied by this operator into dr. So this mathematical property will be useful when we develop quantum chemical methods. So any function can be expressed as a linear combination of eigenfunction of any quantum mechanical operator.